This is going to be an introductory lecture to the Independent Samples T-Test, Chapter 8 in our statistics class. So let's compare the Independent Samples T-Test with the Paired Samples T-Test. So you'll recall in the Paired Samples T-Test, Chapter 7b, we had two columns of scores, but they represented pairs. Like maybe we had repeated measures before and after scores for each individual had two scores, a before score and an after score, or maybe we had matched pairs where we had like the top student in the class compared with the top student in a different class, but we would compare those two individuals so the data came in pairs, or natural pairs like mother-daughter or husband-wife or something like that. And you can see that here in this example. You can see that in the Paired Samples T-Test, each person in sample 1 had a connected person in sample 2. And so this one, it could be that this is a before data point and this is an after data point. Or it could be that this is a mother and this is a daughter. But either way, each one had a connection with someone, or each individual had two data points within themselves. So now in the Independent Samples T-Test, we'll see in the illustration that these are completely different. You can see even that in sample 1, we have a different number of individuals than in sample 2. And we can see there are no lines connecting them. Like it might be there's an off chance that someone knew someone in the other group, but that's not what we're talking about. These groups are independent. Even if maybe these two people know each other, they're still independent because they're not systematically connected. Whereas in the paired samples, every data point has a direct connection to a data point in the same row, so to speak. And so in the Independent Samples T-Test, Chapter 8, two columns of scores represent totally different individuals. For example, one group of individuals receives the medicine and the second group of individuals receives the placebo, the fake medicine. So what are the differences among the tests we've studied so far? Well, first off, we started with the Z-test, in which population 1, the treatment condition, had one column of sample scores. We labeled it X, just one sample of individuals representing the treatment. And then we had population, we've always been calling population 2, but I'm changing to population 0, so we remember it's related to the null hypothesis. It's compared to a general population with a known mean, mu, and a known standard deviation. So we just use that Z distribution. Then we started with a one sample t-test, and in that situation, population 1, well, we still had a problem with one column of sample scores, one sample, and it was representing the treatment, but we were comparing it to a general population where we knew the mean, but we didn't know the standard deviation. So we had to estimate it from the sample. In the Paired Samples t-test, we had a problem with two columns of scores, X1 and X2 for each individual or pair of individuals. And we were comparing it to a general population with mu equals 0, no difference between the pairs of scores. And then we had to estimate, it's a t-test, so we had to estimate the spread. And now we're in the Independent Samples t-test, and it might look kind of like the Paired Samples t-test because the problem still has two columns of scores, X1 and X2, representing totally different individuals. But now we're comparing it to a null population where the mu equals 0, and we're looking at this 0 as representing no difference between means, which is a little bit different than no difference between pairs of scores. So how would we make these decisions? So what should you look for when deciding what test to use? Well, first off, look at your data and see how many columns of scores there are. And if there's just one column, then you continue on and ask this question. Does the problem give the population mean and the standard deviation? If the answer is yes, then it's a Z-test. And you use the Z distribution. And if the answer is no, it's a one sample t-test and you'll have to estimate the spread. If you ask this first question, how many columns of scores are there, and you see two columns, then you have to go on and ask, are there two scores per individual, like before-after scores or mother-daughter scores? And if the answer is yes, two scores per individual, then you have a Paired Samples t-test. But if the answer is no, this is an independent samples t-test. So let's go through some examples. First problem, a researcher randomly assigns a group of 25 unemployed workers to receive a new job skills program and 24 other workers to receive the standard job skills program, and then measures how well they do on a job skills test. What do we have going on here? Well, this is an independent samples t-test, and we can tell because it has two different samples, 25 unemployed workers and 24 other workers. We can also tell because we have even two different sample sizes here, so we know they can't be paired. Number 2, a researcher measures self-esteem in 21 students before and after taking a difficult exam. So you can't even see the data, but you do know that each student has 2 data points, so you're looking at a paired samples t-test. A researcher tests reaction time of each member of a group of 14 individuals twice, once while they're in a very hot room and once where they're in a normal temperature room. So here we have a situation where we have a sample size of 14, but we're getting 2 scores from each person, once when they're in a hot room and once in a normal temperature room. And so once again, we have a paired samples t-test. Number 4, a researcher compares the number of potholes on Navajo Nation roadways in 2023 with the number of potholes on Navajo Nation roadways in general. The mu is known, but sigma is unknown. In this case, since sigma is unknown and we have to estimate it from our sample, we have a one sample t-test. So let's continue. Oh, one more problem first. Dr. Barsa compares liking for video games between teenaged boys and teenaged girls. Here we have an independent sample t-test because it doesn't suggest that each boy is paired with an individual girl, and we know that boys and girls are 2 separate groups, so here we have an independent samples t-test. So this is what our paired samples t-test might look like with its data. We might have teen girl 1, 2, 3, 4, 5, 6, etc. with their before-after scores, and we would calculate the difference, cross off the before-after scores like that, and this is the column that we would use to get our sample mean. Likewise, the number of logs chopped between fathers and sons, well, we would calculate the difference, and we would use this for the sample mean and cross off these data. So that's what it looks like when we're doing the paired samples t-test. So let's consider some examples of an independent samples t-test and what this problem would look like. And so the question that's asked is, do people who write about traumatic events have different levels of physical health than people who write about a neutral event? Use the 0.05 significance level to test the hypothesis. And this information is actually adequate to allow us to solve the problem. We have sets of scores for 2 individuals. In a nutshell, what we would be doing is, get my pen here, is we would be calculating the mean. I'm not going to do the math, and we'd be calculating the mean for this group of people. We can tell they're 2 different groups. In fact, we have 6 people in this group and only 5 people in this group, so we know they're different. And we just want to see, are those means different? Do the means differ? In other words, M1 minus M2. Is that significantly different from 0? And so we would go ahead and we would calculate the sum of the squared deviations. And we'd calculate the standard deviations for this group. We'd get the sum of squares, and we'd use that information from both groups spread 2, kind of get our variance for both groups, spread 1. So this is conceptually what we're doing. We're going to use the information from both groups to calculate the spread for population 0, for the general population. And so that's essentially what we're doing. We're seeing, is this difference, M1 minus M2, is it different from 0? We'll do lots of examples of this so it'll make sense. So now let's look a little bit more at the underpinnings of this. So rather than comparing different scores for pairs to a hypothetical population, that's what we were doing before. We were comparing these different scores in the paired samples. We compare the difference between two means, and this is really an important distinction. So now we don't have one mean anymore, we have two means. And this is what we're looking at. If this is the mean right here, this line represents the mean for population 0, the control group, and the treatment group, and the treatment group mean is right here. We're looking to see, well, what does this difference come to? How different are they? Are they different enough? Is this overlap too big? Or are they different enough that we can say, yeah, this treatment group is definitely different from the control group? We have a new comparison distribution then. It's called the distribution of the difference between means. And it's hypothesized, it's our mad scientist again, who had a single population, drew out an infinite number of samples, calculated the mean for each, subtracted one from the other, plotted it. It's that whole theoretical idea. And so there's our main population, our general population. We drew our two samples, right? We took mean 1 minus mean 2 equals 15 minus 16 equals -1. We plotted that. We did it again, plotted it, did it again, plotted it. So let's look at this in a different way. So we have our two samples that we've drawn from some big population. One of these samples gets the treatment, and one of them gets the placebo. All right, and we're actually calculating the difference between these two means. So we're interested in knowing if we subtract mean 1 minus mean 2, and that's the distribution of this difference between means that we're actually using for our statistical test, and we're assuming that the difference will be 0. There's going to be no difference. So we're trying to see if this difference, mean 1 minus mean 2, is falling into this tail of the distribution. And then let's always remember that these are representing populations. So whatever the sample size is, n equals 10, n equals 8, maybe we have something like that. Well, they're representing a population, groups of n equals 10 and n equals 8. So we're always interested not just drawing conclusions about the sample, but drawing conclusions about the distribution. And of course, both of these groups represent larger populations, n equals 1, that is to say individuals. And so this is what we're really interested in. Is this population really different from this population? That's our question, but we're using all of this information from our samples, this mean 1 minus mean 2, compared with this distribution where there's no difference between these two means. So as always, our biggest challenge is determining what are the characteristics of the comparison distribution. And in particular, as you know, the biggest challenge is always in identifying spread. Let me just get my pen here. Spread is always the biggest challenge. That's always where we're doing the math, because spread makes a difference for determining where our calculation is. So just like in the paired samples t-test, the mean mu is going to be 0. In this case, it means there's no difference between the sample means. We're using the t-distribution again because we're still estimating the variance based on our samples. But we've got kind of a big process for figuring out the standard deviation for the distribution of means. And you'll remember this SM, that S is just referring to the estimated standard deviation. So that's what we're figuring out. So here's an example of how the comparison distribution was worked for all of our different tests. So when we had a z-test with n greater than 1, we were just comparing the mean with this population where this information was given. We were just using the z-distribution, mu was given, and we calculated sigma m by just taking the square root of the variance divided by n. In our one sample t-test, we were still using the mean. I did put the formula here, but just the same, we had to calculate it usually. We were comparing it with where mu was known, but standard deviation was not known. We were using the t-distribution, now normal, based on the degrees of freedom. Mu was given, and the standard deviation, estimated standard deviation for the distribution of means was based on the square root of our estimated variance divided by n. So a really similar formula. Then we had our pairs samples t-test where we were using m difference, the mean of the difference scores between all of those groups. So that's how we calculated the mean now. And we were comparing it with a mean difference in the population of 0. Here's the center. And in order to estimate the standard deviation for the distribution of means, the formula was just the same, which is why these two are combined into one chapter. And now in the independent samples t-test, where the mean is going to be mean 1 minus mean 2. So we're going to calculate the means for both samples and calculate the difference. All right. And the center, we're going to use the t-distribution. We're going to use mu equals 0. It's not mu diff anymore because it's those difference between means. This just means in the null population, there's no difference between the two means. And we're going to calculate or estimate the variance based on this sort of lengthier formula, the square root of variance pooled divided by n. So what is the pooled variance? Well, the pooled variance is just akin to the average of the EVAR, the estimated variance from each sample. So we want to use all the information we have to figure out the proportion of variance for the population. So we have to take into account all that information. So if the sample sizes are equal in each group, in the condition 1, the treatment group and the control group, then we can just take the average. But if the sample sizes aren't equal, then we have to weight them proportionally so that the sample with a larger number gets more weight, gives us more information. So you might consider the pooled variance like this. This circle represents the total variance. And let's imagine that in condition 1 we had 14 individuals. Well, we'll take the estimated variance for that group, but we're going to weight it based on the fact we want it to have more impact because there are more in that sample. And we'll take the estimated variance for the control group. There's only 11 in that group, and we'll just weight them proportionally to get information about the entire variance. We do it formulaically. This is a really important step. We do figure out the variance for each sample, just like we do in the t-test. We use the estimated variance, degrees of freedom included there. Then we figure out the proportion of the sample in each condition. So we take and figure out what percent of the total number of individuals is in each condition. And then we multiply the proportion by the EVAR for each sample and sum them up to get this pooled variance. And we'll work out these formulas in detail. So the next slide is a lot of formulas, but we'll work it out in detail. So this is what the formula is going to look like for calculating spread. So remember, in the one sample and paired samples t-test, EVAR was just SS over DF. VARM was just EVAR divided by N. And the standard deviation for the distribution of means was just the square root of VARM. In the independent samples t-test, we're still going to calculate EVAR, but we're going to do it for each sample. So we'll have EVAR1 equals SS1 divided by DF1, and the same for EVAR2. Then we're going to do another calculation, the proportions for each sample. And so the proportion for the first sample is the degrees of freedom for the first sample divided by the total degrees of freedom, and the same for proportion 2. Then we're going to calculate var pooled by multiplying the proportion for each sample times the variance for each sample. To calculate the variance for the distribution of means, we'll have a two-step process. We're going to calculate var for sample 1 by taking the pooled variance divided by n1, pooled variance divided by n2, and then we're going to take the combination of those two and divide by n. Take the combination of those two. We already did our dividing up here. And then finally, we're going to get our standard deviation by taking the square root of var, just like before. So what other differences exist? Well, in step 1, we'll be defining populations for each condition, and that's different from the textbook, but I think it helps to make it more clear. We're also going to shortcut the hypotheses like this. We'll just be saying for the research hypothesis that mu would be greater than or less than or not equal to 0, and for the null we would just state that mu is different from 0, and that's referring to the mean difference between the two sample means. In step 2, we've already gone through this. It's going to be the same as the one sample tests. In fact, the paired sample test specifically, except we're going to calculate spread differently. And we went through that on the last slide. In step 3, we're still going to use that calculator tool to find out T alpha, the cutoff point. For degrees of freedom, though, we'll use the sum of degree of freedom 1 and degree of freedom 2. And we also will identify the tails based on whether we're predicting that the first mean would be higher than the second mean, or the second mean would be higher than the first mean. And so if you predict the first one is higher, it's a one-tailed high test. We'll calculate the t-score using exactly the same formula, except we're going to take mean 1 minus mean 2 and divide it by sigma m. And we'll talk about that minus 0 as a theoretical framework when we run through the little examples. And in step 5, it's exactly the same for determining whether to reject the null. And we'll just write the concluding statement in clear language. So in conclusion, the independent samples t-test compares mean scores for one group of individuals with mean scores for a different group of individuals. The comparison distribution has a mean of 0, meaning there's no difference between the mean scores for each sample. We estimate the variance from both samples to calculate the spread of the comparison distribution. And the t-sample score is calculated by subtracting mean 1 minus mean 2 and dividing by spread.